Hello everyone, and welcome to alt.net January, the first one of the new year. So if you're here, chuck a comment in so we know someone's listening. I'll just put a comment in myself to see. There we go. So wait a second or two and see how many people we get coming on through. It takes a second for the data to come through, and we sometimes start a few minutes late, so sometimes people don't always turn up exactly on time, which is probably our fault for not starting exactly on time. So let's see, yes, we do have people. This is good. We've got Andrew there and we've got viewers, so this is good. So we have Francis here in person, online person from Brisbane, and I'm in Sydney, holding down the Sydney part of the alt.net, and we have Brooklyn much more excitingly from Vancouver at currently, just after midnight. So she's very kindly agreed to speak to us today, despite the time zone. So I'm at Brooklyn at Yale, Sydney, and I really enjoyed the talk on local LoFi development, so local first movement. And I think you'll find it is very interesting, and that she's also a very good speaker. So I'm looking forward to seeing her talk, and I'm sure Francis is, because it'll be his first time, and I'm looking forward to seeing the second time even too, because it was so good.
Amazing. Thank you so much for having me.
No, thank you for coming on the time zone and everything. So before we get started, we do have a giveaway, so stay to the end, and there's 2 free JetBrains licenses to give away. So I'll, as usual, take down a couple of questions as we go, and I'll ask at the end, and whoever gets it gets a license to each question gets a free license to any of the JetBrains tools. So it's a pretty decent prize, actually. All right, we've got a few people commenting, including one spammer, but some real people as well, so that's good. Lord Teaspoon saying hi, and we've got Andrew saying hi. So let's see. Shall we roll in? Francis, you got any announcements or anything you want to make?
No, not really. Not yet. Maybe. Maybe.
You can think about it.
Not at the moment. Yeah. No.
And I suppose the only other thing is the Programmable conference is coming up in March, I think. So we might have a giveaway of some tickets for that next month, but we don't have any just yet. But stay tuned for that. All right. Well, enough talk and over to the real speaker. So I'll put Brooklyn's presentation up. You ready with the preso?
Yep.
Yep. Here we go. And at the top, because she's the most important. Here we go. And as usual, put your questions in the chat and I'll surface them for Brooklyn and try and interrupt gently to ask them for you.
Amazing. And I'll try to leave some pauses as well to make it easier to jump in. So a little bit of context for everyone else. I'm sharing my entire screen, so I can't see the text prompts as they come through. So somebody will have to interrupt me with questions. First off, thank you so much for having me. I'm really excited to be talking, despite it being past midnight here. I'm going to be giving in order to leave more time for questions, a slightly cut back version of the talk, the Jump to Hyperspace that I gave at Yao. Let's just jump right in.
Nice.
So really this talk, if one thing you're going to get from it as a takeaway is that we've been building apps the same way for about 30 years. And we're treating the tech and the evolution of our tools as trying to extend the same metaphors over and over again. And my job today is to come burst through the wall like the Kool-Aid Man and say that maybe there's a different way to approach these things, and maybe both bring those old ways through to this new world and bring some of these newer techniques into the existing tools. So my name is Zelenka. You can find me anywhere on the internet as Xpeed. As mentioned, I'm calling in from Vancouver, Canada, and I'm the co-founder and CTO at a company called Fission Codes, where we've worked on local first for a little over 5 years now, and all through the stack, data, auth, compute, right now, putting all those things together into a local first computing stack. So think a little bit almost like a AWS Lambda, but it can run everywhere, including offline. Programming languages and distributed systems are my jam, so I'm very lucky to get to work on this kind of thing. And since I'm giving a talk at a meetup, I actually used to run many of the meetups here in Vancouver. So I used to run Code and Coffee, which was a general one, the Vancouver Functional Programming Meetup, and the Erlang and Elixir Meetup. Kind of got paused due to the pandemic. Maybe I'll get back into those at some point. And also do a lot of work on standards, across auth, serialization formats, crypto, etc. And the talk I'm going to give you today is about 40 minutes, probably a little bit over. About a quarter of it is on why the internet is the way it is. Another quarter on why things could potentially change now and why local first is well suited to do that. And then about 50% on how, but really as a high level intuition on how, as opposed to reams and reams of code. The crux of the issue, as you'll see, is that there's a single source of truth in data. And so we often talk about things like having the database. And we now have some techniques that let us relax that constraint. And so what does that open up? So how did we get to where we are today? I often say that 1994 really set the tone. The web existed prior to that, but the W3C was founded in 94, Netscape Navigator was launched. You could even do cellular data at the time. So really all of the major components that we think of as the web came in 1994, and it was really designed to solve 1994 problems. In those days, you had a beige box that lived under your desk. It wasn't even on all day. You'd have to boot it up and boot it down. And it was relatively underpowered. And so if you wanted to receive your email, well, you had to rent a more powerful machine from somebody else that lived somewhere that would stay online. And you'd connect to it from time to time. And it made sense for them then, since you're not using the service continuously, to scale out. So now you have a multi-tenant system, a bunch of different people sharing your server, and now you need auth, right? I don't want you to see my email. You don't want to see your photos, right? We need to know who's allowed to see what. And over time, this one server, gets overloaded. So you need to scale that out. You stick it behind a load balancer and you scale out the auth and the data layers and you do replication behind the scenes. That's quite complex. And even owning and managing the hardware to do that is quite complex. So we created an abstraction, we call it the cloud, and we kind of try to hide away as much of that as possible. And over time, we've introduced now serverless, which is ironically even more servers. And we've extended this basic metaphor for the past 30 years. It has some consequences. As I mentioned before, you have a single source of truth. You like to treat it as if there's a single database. There's the database, not many databases. It's a very server-centric worldview, and there's different roles. So you have to become an expert in DevOps or Docker or Kubernetes or front-end, back-end. And the LAMP stack, which was invented in the late 90s, was the primary way of building applications. You build a .NET app, it assumes that you have something that kind of looks, swapped out different components, but it looks a little bit like LAMP. And even with containerization or even 12 factoring apps, we're saying, well, take this thing as it is, and I want to pretend that my machine is running somewhere else. And that metaphor only gets us so far. And then this final point on here as well, how do we train enough engineers? If we think that software is going to continue eating the world, we're going to need a lot more engineers, unless LLMs take all of our jobs. This is a huge stack for us to have to train people on. So if we can lower the barrier to entry, we can have more engineers being more effective, which means, fortunately, unfortunately, having to change some of these patterns that we do today. When you think about innovation, we're essentially performing gradient descent on the complete solution space, right? Between all the different possible paths we can take, we don't want to end up in a worse spot. And so by being really cautious and by taking tiny little steps, we can make our way up to the top of one of these hills. Though sometimes exploring in larger steps, you end up in a very different part of the design space that's more foreign, but maybe you can find taller hills. Most tech today is really designed around this idea of being industrial, right? Peter van Hardenberg at Ink and Switch often calls this being like an aircraft carrier. And so I've overlaid the CNCF company's ecosystem roughly to scale here. And an aircraft carrier can do a lot of things, right? You can land planes on it, it can go anywhere in the world, you can transport hundreds of people. But sometimes the heaviest tool for the job isn't the right one, right? It really depends on the thing you're trying to do. I've been promised a bicycle for the mind my entire life. It's the exact opposite of an aircraft carrier and works at a very different scale. But as an individual, I mostly get around town on my bike. Sometimes I rent a car. If I'm moving, I rent a moving van, right? It really depends on what goal I'm trying to achieve. And I've never been on an aircraft carrier. I don't need all of AWS for every problem. So we have this whole stack of these specialties. And not only do you have to get trained in every single one of them, or have specialist groups inside of an organization for each of these, it also puts a lot of distance between the developer and the user. And on a mobile device or on native APIs, you have a lot of really powerful capabilities now, right? That haven't really found their way into the web. The browser's getting more and more powerful, but it doesn't do as much, right? You can't persist to disk and expect it to be around, for sure in a year, right? So what are the APIs and what are the components that could make web development more like native development? And even what can we add to native development to not have to deal with all the additional complexity of what is currently termed the cloud, so that we can have faster iteration, focus on our end users, and lower the barrier to entry so we can get more people into the industry. We are only limited by physics, it turns out. So there are some hard constraints that we can't work around. The first is the availability of where compute is, right? So this is AWS's data centers from their own website. And as you can see, in North America or Europe or far Eastern Asia, there's actually pretty decent density of data centers, right? So mostly those places, and this makes sense, right? If you're trying to make money and it costs hundreds of millions or billions of dollars to set up and run data centers, you want to put them in places where there's a lot of customers and a lot of demand, and you can then avoid putting them in places that are uninhabited, right? Which are, of course, places that are inhabited, that have people that are online, that are trying to do things, but are always having to dial over into US East 1. I used to work with a guy from Nigeria who there was no option near him at all. If we talk about population density, in this circle, there's 50 million people just in there, which is how many people we have per data center in North America. In South America, it's about 1 per 500 million people. And in Africa, it's 1.5 billion people per data center. And the one they have in Cape Town is, I believe, the most expensive availability zone, which makes sense. South Africa has rolling blackouts, and they don't have economies of scale, and all of these things. But it doesn't make sense that the furthest remotest one, where you're trying to serve this entire continent, should be have these extra barriers to entry. When so as I mentioned before, I was at Yao. About 2 months ago, I was in Australia, and I flew through Auckland. Auckland to Wellington is about 500 kilometers. And so sending a text message or an image or an email, that distance is pretty quick, right? That's a small distance, especially at the speed of light, or we do about a third in copper, so better in ideal copper in a straight line. But of course, that's not what actually happens. In the ideal scenario, so let's be generous and say that the application is actually deployed in the nearest AWS data center. It's going to make a round trip to Sydney through an underwater cable, chances are. Which is fine if it's something like sending a photo. That's not very latency sensitive, but that is extra time, energy, carbon, and just maintenance on those lines, right? You're using a lot more of the infrastructure all the time. And doing this extra round trip. So we've added each direction about 2,200 kilometers to this round trip. So it should have been 490K. In this case, if you round, it's about 10 times the distance to make a trip to the server and then out to the recipient. And I'm not sure if you remember your high school geometry, but that is not the shortest path. So the two questions are, how can we shorten this path? And in fact, can we get down to 0 milliseconds? Is it possible to get some of these things to the actual physical limit, where unless you need to communicate with somebody else, you can actually get this down to 0, because you don't have to go out to a database that's somewhere else? And can you actually talk directly in this case, the 490 kilometers instead? Chris Micklejohn wrote this great paper, A Certain Tendency of the Database Community, where he argues that as we increase the number of internet-connected devices that we have, the amount of coordination we have to do in our current systems increases massively, and that it's no longer practical for us to assume that there's a single or even small number of globally distributed data centers. We have to break this model of thinking that there's a single place where we have to always go out to the same data center all the time. And again, on the previous slide, I was being generous, saying that it's deployed in Sydney. It's much more likely that it's deployed in US East 1 as the default for an application globally, because that's the cheapest one. That's where they're incentivizing you to put your data. The CAP theorem is often criticized for having a couple shortcomings. So same basic idea, but unpacked a little bit is PACALC. So think of this as CAP++. It says that you have two scenarios that each give you two choices. If you're under a network partition, so you have two machines that can't talk to each other, you have to pick between availability and consistency. So this is to say two machines can't talk, and if they want to be consistent, they can either be down, so they can stop functioning until they both come up and they can handshake again, or they can be available, they can stay up, but be in an inconsistent state while they're still running, which makes sense. They can't talk, so they can't agree on a value. The other scenario is that you've healed the partition. You're under the normal case. So this is the else case. You can be consistent or you can be fast, right? And there are absolutely cases where you want to be down and consistent, down and slow. But I would say for most applications, you want to have 100% uptime. And when machines are actually physically connected, for that to be a fast connection. Right? Again, it's not banking, but for most applications, you want these things. And I'm going to touch a little bit today on a PA-EL system called AutoMerge. So that's always available and always fast. That works at the data layer. I'll also talk about UCAN, which is a PA-EL auth system, which stand in contrast to things like Google Docs, which is a PCEL system. So on Google Docs, if you go offline, you turn your Wi-Fi off, you can't type in your document anymore, even if it's loaded in the web page. It just stops. And there are some people experimenting with PA-EC systems, so ones that are always available, but when you come back online, you have the potential that it'll overwrite the data that you wrote. Also seems less ideal, right? There's a line, a failure on a computer you didn't even know existed. So this PA-EC system is, if their system is buggy, it can at any time overwrite everything that you're doing on your machine, even if you had previously entered it. Think about it as somebody else doing your Git merges for you. So Leslie Lamport, major distributed systems researcher, I guess, said a distributed system is one in which a failure on a computer you didn't even know existed can render your own computer unusable, right? So we want to avoid that. So in a lot of ways, local for software is solving Lamport's problem, because it says even when you are disconnected, your machine continues to work. And if you get bad results from another machine, you can just ignore them. So you're never in a down state and you're never stuck, because the source of truth is always on your machine. And we use fancy techniques that we'll talk about later to make it so that when we heal that partition again, all the data can stitch together automatically, but that each individual machine is in charge of and in control of being able to stitch that together. So finally, we have a new hope. Things are early, but exciting. So as I mentioned before, we've been working on local first, LoFi, as it's sometimes called, for a while, for several years now. And in mid-2023, something seemed to have changed. So there was this article in Wired, and next to Strange Loop, we ran a local first meetup. And we thought, we'll get like 20, 30 people. And then that filled up, and we extended the cap for the event, and that filled up, and we extended the cap for the event. That filled up, and we had 200 people on the waiting list at the end, and we filled the entire venue. So people are now suddenly interested in this. And I look around on Hacker News or just on the web in general, and I'm running into lots of things that are putting local first right on their homepage. So something has shifted in the past 6 months to a year. And my guess on what specifically is that the technology has now started to become mature enough at the data layer that it's practical to use in lots of other places. We see local for software actually in the wild for a long time. It just didn't have a name in some of these cases. So Apple Notes, Figma, Jupyter, and Git are all some form of local first. Git, of course, if you need to do a merge and there's a merge conflict, you have to manually resolve that. Most people think about local first with CRDTs, but this actually does fit all of the conditions of LoFi. A couple things that are explicitly local first. So on the right side, the animated one, Ink and Switch, so the people that coined the term local first. This is Upwelling, which is a collaborative document editor. Think like Google Docs, but with the ability to put yourself into a disconnected mode. So if you just want to focus and write and not have, like in Google Docs, a bunch of other people typing on top of your words, you can just stop that. They can keep typing over there. And when you flip back on, it'll merge automatically all of your changes into their document and vice versa. On the left is a Dropbox clone. So you can do something that's, files and hierarchy and directories and file sharing and private files, all of that stuff, but in a totally local first way without a server involved. So you can always back it up to a server, but it can run directly in the browser. And then at the bottom, Actix does factory automation in a local first way. So in a large factory, they're not fully blanketed in Wi-Fi, and so they need to dispatch robots to go, grab parts, things like that. And they have a coordination problem, right? You dispatch a job, you want to make sure that at least one machine goes and grabs the parts. But if two of them are doing that, they should be, if they get close enough together to communicate, they should communicate and one of them should back off. So solving problems like that in an industrial setting as well. The original ideas of local first, so the original local first post, which I highly recommend, it's very, very well written, proposed these 7 ideals. And seamless collaboration with your colleagues, which is what brings most people to local first, has been basically a slam dunk. It's just better than doing it basically any other way, right? Going through a tunnel and not being able to type into your document is terrible, right? So this solves that problem. No spinners, work at your fingertips, your work not being trapped on a single device, the network being optional, and security and privacy by default. I think these are uncontroversially good things that people like about local first. The last one, security and privacy by default. I would say that there's more work going into this these days. We'll talk about that in a little bit, but it's definitely something that still there are 3 or 4 different ways of doing it, and not one of them has really won out yet. These last 2, the long now and retaining ultimate ownership and control of your data, I actually think these are the ones that are actually like really important sort of socially, right? Like to the society, but we're not gonna have time to talk about them. It's more of like a philosophical approach to software. So it's a little out of scope of this talk, but they go into it in the article. I've also heard that if you think about the arc of history with computing, in the 80s and 90s, we had desktop computing, which was personal computing, then moved into cloud, which was again very sort of industrial, right? Going back to the aircraft carrier, impersonal computing, and now with local first, we have interpersonal computing. It's really focused on collaboration and making things that always work directly and don't have to always go up into the cloud. This does mean that we need new metaphors. So with cloud computing, you can really think of it as a layered cache where the internet is the source of truth and your machine is just one cached version. So we go from the internet down to disk to memory to your CPU caches, and it's just one cache hierarchy. With LoFi, it's a little bit more like P2P or a cellular structure where you have a bunch of peers that there's no single source of truth. They each have a different slice of information because information can only travel at the speed of light, right? So they're going to be at least slightly inconsistent some, if not most of the time. And this picture looks a lot messier than the layered cache version. But when you think about it, you actually only have to ever think about your machine or maybe communicating with one other. And the rest of it, the rest of that picture comes from these individual links of, well, peers. Peer-to-peer networking, some of you are probably screaming in the back of your head, peer-to-peer networking is really, really, really hard, right? When it works, it's magical, doesn't always work. So there's nothing in the model that says that you can't put a sync server in the middle. You can do both, and you can even do both in the same application with a sync server as a fallback if you want. A major advantage is that that sync server is doing very little. All of your storage, data layout, vast majority of your computation is happening on your individual instance. And so your sync servers are effectively, you can swap them out for another. So you have a choice of provider. They just have to be able to store data and retrieve data, of which there are many companies that provide that as a service. When we set out to work on this, we thought, well, it's pretty simple. You put data at the bottom, right? You have a database, and then you have a compute layer. So think of that as your, your controller in a, sort of classic web framework, and then auth, which lives at the boundary of the system, and kind of would mirror something like this. We found that didn't work basically at all, right? We had to rethink how this works because the data has to move around to any arbitrary place and still be secure. It still has to follow the rules that you set out for it. It still has to do auth. So we found putting auth at the very bottom that manages the data and enables data. So doing things like encryption at rest, we'll talk about this in a moment, and capability systems. And then data obviously enables compute because you have to be able to consume compute. And my goal today, again, is to give you a high-level intuition of how these three layers work. There is one other layer, managed effects or an effect system, which is really how do you talk to the rest of the internet? So not a local first system. How do you cross between local first and not local first? That's a little, again, a little bit out of scope for this talk, but there is work going in that direction. So welcome to the jungle of distributed systems. You work on the internet. You're automatically a distributed systems engineer, whether or not you have formal training in it, or as I like to call it, disorderly systems, because it's literally things that are out of order. One of the challenges of moving to working in distributed systems is we're trained to work in a very sequential way of thinking, right? You have a sequence of steps and they will execute in this order, right? In the vast majority of programming languages, right? And then you have to take that code and put it in a networked model where things can break, things can move out of sequence. Or to put this in pictures, here's your user agent. You have TCP, HTTP, and JSON coming as a request. You send that out to the network. And now you have to deal with repeat messages and unbounded latency and out of order delivery and partial failure. Partial failure really being the killer, where literally as the name sounds, you wrote into one database, but the second system failed. Do you roll back the first one? Did the second? Have you just not heard back from the one that failed? Like, did it actually go through? You don't know, right? So it becomes this really complex picture very, very, very quickly for what should be a simple problem.
Brooklyn, got a question for you.
Yeah.
And I'll just pop it up here. So regarding the sync scenarios, this is to my experience of C# of T, the questioner, merging usually requires lots of context to have a fine merge with no limited issues. Wondering how can this be done automatically?
Yeah. So we'll talk about this in more detail later in the talk. There's a whole section for this, so we'll get there in a moment. But the short answer is the sync server is not the one doing the merging of the data. It's your instance will. So the sync server just receives events and rebroadcasts them to everyone else, and then doing the merge happens on each individual instance. But we'll talk about how the actual merge works, and it has its whole own section. Other questions while I'm paused?
That's it for the moment.
Okay, great. So we will get there shortly. Okay. Actually, I think in 2 slides. Problem that you run into is how do you do merge, right? So obviously the one on the right is Git, and you do a manual merge, and the one on the left is Apple Text Edit, which if you make changes on 2 devices and then resync them, it will ask you to drop completely one version or the other. So there's no merging at all. You have to pick one version or the other one, and that's kind of terrible. So the good news is that there's a solution to this problem, and the broad context of these. So CRDTs are the ones that are really known, but there's a few of them, and we'll talk about CRDTs specifically in a moment. But the COM theorem tells you specifically which problems can be solved in a coordination-free way. So it says a problem has a consistent coordination-free distributed implementation if and only if it is monotonic, which is quite a mouthful. So I'm going to break that one down for you. Consistent means that when everybody gets all of these events, so using that sync server example before, the sync server doesn't need to know anything about what it's storing. It just needs to know like, oh, I got some events I'm going to rebroadcast them. And it can even rebroadcast duplicates. That's fine. Coordination free means that we don't have to agree on what's in the set or what's out of the set, other than just accepting, these are, we're not ever going to remove things, so we don't have to agree on them. We're only going to add information, which is why it has to be monotonic. So the translation of this is, when we all have the same messages, we'll all have the same state. We'll all have the same view, if and only if we can express this in a monotonic way. So what does monotonic mean? Two common examples. The max function is monotonic. So it says if I have the max between 1 and 2, the max is 2. 2 and 42, max is 42. The max of 42 and 10, still 42. Max of 11 and 42, it's still 42. So the reason that this works is that the number is only ever going up and it never goes down, right? So the fact that it's monotone just means it goes in one direction. Or set inclusion. So I have a set and I add items to it. So I add 1, I add 9, I add 4. I try to add 9 again, but it's already in there, so that gets deduplicated. I'm only ever accruing information. Information is never leaving. This means that I can take any set of, literally set of events and merge them together. And I don't have to worry about what order they came in. They just stitch together automatically. Another example, and to give a more of a distributed systems case. So here's Alice, Carol, and Bob, and they have time running left to right. And they each have a paint color, and they're all going to agree by the end of this without having to all get into a room together and say, like, do we all agree on, that it was this version, by mixing paint colors. So this isn't only an analogy. You could very easily write this as a CRDT algorithm. And here they are sending, very sort of, out of order, and this long yellow line has a lot of latency on it. Very messy set of messages, including duplicates and redeliveries, all of these things. And at the end, we all agree that the color is brown. When I combine yellow and blue, obviously I get green. When green gets sent back, so it's not that blue has to say, oh, well, I know that I got something from yellow earlier. It just sends it out to whoever it's connected to, whoever it knows. Green already has a yellow component, so nothing happens. And so same idea for the rest of these. And that really long, delayed message, well, it's already a part of brown, so that's fine too. Nothing actually had to get updated there. And even these can happen in separate sequence. So we can combine blue and red, yellow and blue, right, to have different colors. And then at the end, if they hear about all the messages, they'll all come together on brown, right? And we could send the brown around as much as we like after. We don't have to know who has what. We can just broadcast as much as we want. This doesn't only work at the very low levels. You can also clean this up a lot. So this is an example of auto merge, which is a JSON document editor in for JS. There's also a Rust implementation that compiles to WASM. And the idea is that the interface looks basically like you're doing just normal editing, except you wrap it in this auto merge function. And you can do, increment counters, you can map keys, you can do nested maps, update their values, change things in lists, all of this stuff. And under the hood, it's doing all of that monotonic stuff that I was mentioning before for you, so that you can be offline, do a bunch of editing concurrently with other people, come back online, and auto merge under the hood will stitch all those events together and render a consistent view. Now, by consistent, I mean everybody will see the same document at the end if they've all seen the same events, right? that doesn't mean that it's semantically correct. So a lot of work goes into making them be as unsurprising as possible, right? So it's very, very easy to make, I'll just use CRDTs as the classic example, very, very easy to make CRDTs that will give everybody a consistent view, but that, maybe each letter is interleaved, let's say. So a lot of work has gone into making algorithms where if you're writing concurrently, the sentences will be separated. And so you'll have Alice's sentence before Bob's sentence, and they'll be complete sentences. Then you can look at it after and go, we should probably remove Bob's sentence because it doesn't make sense anymore in the broader context. Access control. So static access control wherever the data lives. So even if you have data that lives in a place where you trust who's running it, right? So it's somebody that's you think that they agree to all the rules. You can always have what's called a Byzantine agent. So it's either malicious or buggy. So buggy implementations can cause access control problems. And so you always have to be able to plan for revocation, but ideally you get rid of the revocation case as much as possible. You just say, you know what, let's just make that an impossibility for as many actors in the system as you can get. One of my all-time favorite quotes is that cryptography is a tool for turning lots of different problems into key management problems, which is on one hand horrifying because key management is super hard, but if you solve it, you now solve it as an abstraction for all applications, right? So it's a big lift, but once you've lifted it, it's solved for everyone. In this new world where any data can be merged with any other peer, really you have not connected nodes of machines, you have connected nodes of data. And so you basically give different people slices into this global connected mesh of data and say, this person's allowed to see this slice and that person's allowed to see that slice, and they overlap in this way. To do read control in a local first way, you have to use some kind of encryption at rest. So on disk, when not in use, it's fully encrypted. You can store it fully encrypted. Nobody can read it unless they have the key. One mechanism for this is called a crypttree. And so crypttree is an established concept, and there's also a temporal crypttree, or sometimes called a dark forest. So every file, this works on any graph data. We'll just use a file system as a simple example. So every file has its own key, completely randomly generated, and every directory has keys for all of its children. So it has both a pointer to the child and the key to decrypt it. The upshot of this is if I give you the key to the photos directory, you can't read the docs directory, but you can walk down and see the alt.net and the vid.mp4, because you can discover those keys as you walk down. And so this lets you slice things in a way that works exactly like how access control works in Dropbox or Google Docs, which is say you get access to a directory, you can see everything in that directory. You also probably want to give access to things over time. So because we're just throwing events, throwing updates into the sync server, and you can't guarantee that they're going to evict that data, you probably don't want to give access to things that go back, to the very beginning of this file system. In this case, you probably want to say at this point onwards. So every file, in addition to having its randomly generated key, you actually use that as a seed, and you hash it for every update. So each update then also affects its parents, and that cascades up when you want to do writes. This is called a temporal crypttree, and it's actually a little bit more sophisticated than this, where you can give, using certain hashing algorithms, the ability to only read, say 10 updates and nothing after that either, and nothing before the point where you shared the key. So that's access control in a static setting. If you want to do mutation control, so writes and commands, people usually reach for an ACL, access control list, which is what we're all familiar with. You have a user and a service, and when they send the request, there's a software bouncer that looks at a list and says, hey, are you on the list? Show me your ID. Yep, cool, farmer is on the list. You're allowed to access this service. And this is really great in some ways because you've split this up into 3 stages, right? The access control layer can just be plonked in front of absolutely anything. The downside is that these 2 aren't in control. We now have a dependency on a service that runs somewhere, so it doesn't work offline. You have this single source of truth, and that document, the list the bouncer's checking in the metaphor, has to be synced around, and it can get inconsistent. And this is actually a real challenge for syncing access control and policy management broadly. And there's ongoing research into how to make ACLs work and to really scale up. Because you end up with this bottleneck in the middle, and you have to figure out how to scale that bottleneck. It's the same problem as scaling a database. Capabilities are the other main branch of auth systems. They unfortunately really came, they go back to the 60s, but they really got codified in a sort of modern workable way after the web had already been created. So it didn't end up in that, those small step increments. The way this works is you have a user and a service, and it's more like going to the movies where you have a ticket to the movie. The ticket was issued by the movie theater. They don't have to ID you on the way in. You just show them the ticket and they go, oh, cool, great. Theater 3, you can go see the film. This puts these 2 in control without an intermediary. All of the required info and the source of truth lives in the ticket that you send along with your request. Where the movie theater metaphor breaks down a little bit is you can make copies of these tickets, and you can even attenuate them. So instead of being able to write to the entire file system, maybe you can only write to a certain directory. That's attenuation. So you can always go down in power. And you can send these copies to somebody else who can then now also access that service. And these don't have to be too scary. We've implemented this on top of JWT. So it's basically JWT with some extra checking rules to make it local first and run completely offline. It requires that you identify who issued it and who it's going to, the links from this diagram, basically, what they're allowed to do, and then a proof chain. So pointing at previous ones of these that prove that you're allowed to continue this chain. The original owner of that resource gave you the ability to do something, and then you hand it off to somebody else is the chain. This has additional advantages. We've eliminated a role from, for example, this is the OAuth sequence, which is, I believe, it's been a while since I've counted this, but let's call it 12 steps, which are basically set up with the authorization server application and user. And then the application wants to use it. So application, auth server, and resource. And switching from ACLs to capabilities lets us eliminate this auth server and talk directly, which simplifies the model. We have 4 steps. We have the setup here and the use of it there, the invocation of it there. So that's a very, very high level introduction to UCAN, which is the JWT-like version of this. And finally, so I said before, we're going to talk about auth data and compute. Let's talk about compute. So compute is sort of a newer topic in local first because you can compute anything. When you have the database on your machine, you can compute anything you need on it. The downside is sometimes things are really expensive to compute locally. Maybe you're on a low-powered, smartphone, and you need to, run an AI model. Maybe you need to kick that off to the cloud, and you can always run it locally, but you need it to go out to, maybe you'll get a performance boost. So it's this almost like caching, but for compute. So there's this very, very old idea, code as data. Literally goes back to the 50s. And hey, good news, we now have WebAssembly, which is a deterministic sandbox execution environment that serializes to binary. Great. So the fact that it's deterministic is really important because it means if I run it or you run it or we run it in 10 years, we'll get the same result on the same inputs. And sandbox, which means I can run it anywhere safely. It's not going to damage somebody else's machine. We can wrap together arguments, the WASM, and then a little bit of scheduling information into a task. We then take the hash of the task and use that as an identifier on the network. And that doesn't invoke it immediately. So by analogy, it's a little bit like having a closure in, say, in this case, JavaScript. If I just pass around a reference to it, nothing happens. But if I put the parentheses on it, then it actually runs in this case, an alert. In our case, you have to actually sign over it and say, hey, please actually run this thing. And then you have a cryptographic signature over that. So in the browser setting, we use passkeys and the Web Crypto API to do this. So there's actually, it's just using browser APIs. And then outside of the browser, you can use whatever you want. So OpenSSL, things like that. You have a receipt at the top. So when you receive the result back, you get a pointer back to, hey, I ran this task. Here's the values and further things I want you to run after this, and any trace metadata afterwards. And because this is deterministic and sandboxed, that means if 3 people run it, they should get back the same values. And so the receipts should match as well. This also lets us link together different bits of computation. So distributed invocation and distributed promises. So here's 2 calls to the same functions. This is a WASM blob that we're going to invoke. We're going to call the add one function on it with the number 42 in the top case. In the bottom one, we're going to put an await in there. So that's a promise. And this both lets you link them up in advance and say, hey, I'm going to build up a graph of computation and then send them off to somebody. Or if something is already running, let's say it's going to take 10 minutes to run, and you're like, you know what? I don't want to have to wait around for that to finish and return something back to me and incur all of the latency for that to come back. I'm just going to start issuing commands and saying, when you finish, pipe that into this other thing. So this is called distributed promises, which is, again, goes back, for quite a while, at least 20 years. And that lets you build up these graphs of computation, where it doesn't matter if you submit them at the same time, or if one of them had already been run, 10 years ago. You can just describe this and send it out to the network, and the network will figure it out. Or your local node will figure it out, depending if you're connected or not. You'll notice that there's something similar to CRDTs here, where we're saying, don't worry about the specifics. We're going to have some abstract properties that you have to follow. In this case, these await connections, kind of like how we have to be monotonic in the data case. Here, we're saying, you're not going to be able to say where this runs, just that it runs. And then the network can do smart scheduling and figure out where these should run. So one example is maybe these are, Alice and Bob, and Alice is going to run these 2 steps, and Bob will run those 2 steps. And automatically, when the first step finishes, it'll pipe over to Bob, and then Bob can continue. And on that bottom CRUD update on the reports, he'll have to wait for Alice to send the last input. So we can do very efficient scheduling. Anytime you're going over the network, you're incurring latency. So you have to decide and use heuristics. Is this worth for me going over the network boundary, which is potentially slower, and potentially I might not get a result back. They might go down, or I might get disconnected. So there's a little bit of complexity handled by the system there. Now, again, this being deterministic means that at each step, so as we're calling separate functions in these chains, we pipe out receipts. And so it continues straight through, but we get intermediate results, which is great because then we can reuse intermediate results in other computations. So if this other WASM that's grayed out on the right is the same as the top one, but it gets called by a different receiver, well, that's fine. We can just reuse that receipt, even if it's wasn't run by us, as long as we have access to a network where we can identify the task by its hash. We can say, hey, did anybody run this thing? What was the result? And skip running it completely. So you get caching at scale. This has a really interesting effect that is only just now starting to get explored. When you try to parallelize problems, what you want is that your throughput will increase linearly, right? So the more machines you add to a problem, the more throughput you'll get. But we know that in most cases, they don't parallelize perfectly. There's a little bit of coordination overhead, right? So it's called Amdahl's law, where you get a little bit of a drop off. It's actually, in most cases, there's actually a peak where you can only get a certain amount of parallelization, and then it actually gets worse because you're spending more time coordinating all these machines, and again, maybe they get disconnected and you have to wait around for them, all this stuff, or they send broken data and you have to do retries, et cetera, et cetera, et cetera. But by using this caching mechanism, we can potentially actually get the opposite curve using something called global adaptive optimization, which is a little bit like BitTorrent or IPFS, where the more people that are hosting, Ubuntu ISO, the faster you'll be able to download it. Same thing for results from computation. So you can both skip compute that's been run before, deterministic compute, and the more people that have run things, there'll be a power law, right? So there'll be a few things that are very, very popular and get used in a lot of applications. Those will start to get resolved instantly. Or if somebody's, say, resizing a particular image a lot, the network will be able to cache that for you automatically, and you actually get better than linear scale. The more people running, the more people participating, it actually strengthens the network and makes it faster. Some people have started calling this run once and run never again. So you now have this reverse lookup table. I have the hash of my input, give me the cached output. It gives you things like instant AI. Somebody's asked a particular prompt, in whatever your cache period is, just go to the network and ask for it. Or somebody's asked for a certain image to be generated. You can look that up with the reverse index. You can get moderation and tagging automatically on content. In this movie, is this, what is it classified as? Is this, what genre is it? All of these things that can be quite expensive to compute. Now you have a cache for it. You can do transitive trust models like eigentrust that say, if Alice trusts Bob and Bob trusts Carol, you can calculate the trust relationships between them. So how much should I trust Carol now, as I guess Dan would be the next in that sequence. Resizing images, thumbnails, cropping, and durable execution everywhere. So even if you fail halfway through execution because you ran out of memory or there was a power outage or whatever, you automatically can resume and even reuse results that somebody else was consuming. So your machine goes down, it catches fire, you have to start on another machine. As long as you can get the previous cache, you can resume from where you were instantly. So here's a demo. We actually have a prettier version of this now, but this is sold. This will be in 720p. So this is the low res version. So the description of these is all just in JSON. And we have some awaits, and we're going to do some blurs and crops. And so we run the first workflow. And it takes a little bit of time to run. It downloads the image and it's cropping it. Actually, that image under the hood is quite large. So it crops and then does a rotation on it. And we even kill the node that's running it, so we don't get to the blur. So this is the durable execution step. So that failed because we had a network partition against the thing that was actually running it. We go to rerun, start again. It didn't have to do the crop and rotate again. It just pulled those out of the cache and blurred the image. And workflow 2, you'll notice, has crop and rotate 90 as well, and then grayscales. It didn't have to do the crop and rotate. Those happen instantly again, and can reuse those for the grayscale. So pretty straightforward. So that is auth data and compute. Where do we go from here? We've been told our entire careers, for a lot of us, that you have to pick between being a front end, back end, or maybe a DevOps engineer. And just like in the Matrix, what they didn't show you was that there was actually a third hand, a third way that LoFi says that's a false dichotomy. There's another way to go forward. This is a new design space, comes with new constraints. So in the 80s and 90s, we had personal computing. You owned your software. It came on a floppy disk. You had full control over all of your software. Then we moved to cloud computing. We could do much more powerful things. You could, have distributed watch parties. I think this is the Apple example gives. But you're just renting software from somebody else, and they're in full control. And now we have local first, which is kind of a bit of both, but it also has different, some different axes of freedom from those other two, right? We get offline capabilities and the ability to store stuff on any data, any sync server, any storage, but there's also other trade-offs where you maybe need to drop back down into cloud or personal computing. But LoFi is early enough that we haven't actually figured out what all the degrees of freedom are and what all the trade-offs for that will be. So I'm really excited to see what people are going to do with it over time, and that's the end of my presentation.
Thank you very much, Brooklyn. We've got a few questions for you. Let's see the first one. So this is from Andrew. So from a corporate's perspective, what's the incentive for peers to participate in this distributed local first network? Or, as a business, do I have to employ a park of my own bare metal machines again?
Yeah, fantastic question. So you can do that. The idea is that it doesn't matter where your data lives. You could still use a third-party service and back up your data. You can still, in fact, people have built local first systems that back up their data to S3. My company has done that. For example, we've done both S3 and IPFS, for example. But the local machine always ultimately has control over its own data. So that's only for the backup portion. You should always have a local copy of at least the portion of the data that you need to work on sort of day to day. So you don't need to set up your own bare metal servers. The point is that it abstracts away all of those concerns and makes it much simpler to run such a server.
Cool. So we got someone claiming that you can't fit anything on a floppy disk. I think you could actually. There was certainly a period where you only had floppy disks. So yeah, this is the exact comment is Brooklyn said in the 80s you had your floppy disk. She's obviously too young to know. You can't fit anything on a floppy disk.
Right. Yeah. Oh no. I definitely remember having to feed them in one at a time, pull it out, put in the next one. Something went wrong. Start again. Yeah.
Yeah. There was the modern ones, and then you got one on like the fourth floppy disk that was corrupted, and then you had to write back to the supplier to post you out another one. And have we got any more serious and sensible questions here? Besides, there's a lot of chat around old computers and floppy disks here. Yeah, Windows 95 of a stack of 1.4 meg floppies. All right, what about some more questions on the talk? Any at this point?
I've got a few questions actually.
Go for it, Francis.
Yeah, I think some of the things you described, I guess in distributed systems, we can also use things like consensus systems to kind of reason about our data and so on. But I think the stuff that you mentioned, I'm guessing you've kind of taken some of the contention, like resync issues, out of that equation. So I presume it's much faster in theory to be using some of the things that you described rather than consensus algorithms out there. That's kind of
Yeah.
on production at the moment.
Yes, yeah. So if I'm going to wind way back because I don't have an index in this view, unfortunately. So you have this trade-off that's implicit, right?
Do you want to share again, or?
Sorry, I'm still looking at the thing. Yeah. Do I have to hit a button? I do. Okay. Share screen. Okay. So do you see the slide again?
Yep.
Yeah.
It's up.
So there's always this trade-off, right? So with consensus, a consensus-based system is PC EC, right? So under partition, you're down or you're going to lose data, right? So even in say Paxos, right? You have voting periods, and anybody who misses the vote, they missed the vote. Too bad, right? And it's definitely not low latency because you have to incur just the network overhead and then all of the extra messages that go back and forth for that. So you're actually collecting from everybody. At fastest, you'll be with the slowest person, right? Or the slowest machine. And it requires multiple machines to all agree. So it's not, obviously it's not available, right? It doesn't work offline. So for most applications, a big part of the thinking in LoFi is, well, now we have ways of doing data that automatically replicate everywhere. We don't have to wait around for consensus, except for things that actually need it. Actually, I have a post slide here. There's a fantastic talk at Papers We Love last year, 2023, by May Milano, where she talks about mixing consistency levels. So everything I've talked about today is in eventual consistency, where at some point we'll all get the same messages, and then we will have converged on the same answer. Right? You may only and those problems very much fit into this whole monotonic paradigm. But not all problems can be expressed that way, right? So doing financial transactions, you should not do financial transactions in an eventually consistent way. Like, just don't do it. You need to make those linearizable, which is the strongest possible consistency level, right? But you can mix them. So you can have part of your system be eventually consistent and then detect, oh, I need to be actually linearizable. I'm doing now financial transaction and I need to go into lockstep mode with everybody else for a little bit here. And then I can go back to my, beautiful freeform world where I can disconnect and reconnect at will. The idea is that the underlying framework should be able to know how to switch between the two. But yeah, there's always this trade-off between consistency and speed and availability. You're stuck with those three.
Okay, yep. And I guess my other question is, obviously I've not read Martin Klipman's book, but I've seen all his videos, and obviously, I think a lot of my knowledge comes from his books, but also just kind of random articles I've read. But I think, what's amazing about your talk is you've kind of introduced all these concepts that I was not either familiar with or I didn't really know much about it. So where can someone like myself, or I'm sure there are some other users in our chat, where can we find out more? Where can we read more about some of the things that you mentioned today?
Mm-hmm. Yeah, absolutely. So Martin Klipman's work is, as you mentioned, just fantastic. He's a very, very clear writer. And his book, Designing Data-Intensive Applications, DDIA, which I think is the top-selling technical book on Amazon, is fantastic. And it okay, designing data-intensive applications, it sounds like I'm going to be doing some stuff with databases or something, and that's definitely part of it. But it's really like a really solid foundation in here's how to think about distributed systems. So that's a really good one for local first. So Martin actually also wrote the local first post. He's
Oh, did he? Okay.
yeah. He came up. He's one of the, I think there's 4 authors on that. Came up with the term. So the local first software, own your data in spite of the cloud, I think. From Ink and Switch is a really great introduction to that. The May Milano talk that I just referenced is very approachable, very clear, and talks a lot about the consistency levels and uses very practical examples. So that's May Milano at PWL, Papers We Love. Distributed systems techniques broadly. So I talked about the COM theorem. If you go to bloomlang.org, they'll have more writing about that there. And then capability systems, really fantastic book. I guess it's technically a dissertation, but Mark Miller's Robust Composition. It's about 200 pages, but if you're into auth systems, it's very, very, very well written, and it's actually integrated into a language. So if you're into programming language design as well, it's an interesting read as well.
So, and hey, I might bother you to actually maybe at a later date to send me all those links, and then I can share it with our readers on a later stage.
Yeah, we can put it as a meetup comment, which will go to everyone who attended. So that would be cool. We have one more question as well here from the chat. So how do you go about the change process for devs? The move to Agile was a decade-plus long process of change before it became mainstream. How did you advocate this to devs?
Yeah, fantastic question. There's even Agile, right? But especially with choices of technology, there's the 2 buckets: vitamins and painkillers, right? Or sometimes people will say eat your vegetables, right? As something that you should do, but nobody really wants to. There are major advantages to local first, like encryption at rest, higher security. You can't have a data leak unless somebody somehow breaks, major encryption algorithms, at which point your banking is probably a bigger issue, right? And those are all kind of nice to have, right? Arguably they're really important, but day to day, why would a developer care? The number one thing that people say with local first is it makes their lives makes development easier, because they don't have to write as much code, you don't have to maintain as much stuff, and there isn't this, you go to build an application today and you get it up and running locally on your machine and it's totally working, and then you want to share it with somebody else, and you can't. You have to put it in a Docker container and rent a server somewhere and ship it out to the network and all of this stuff. Versus local first, this example I'm going to give is more in the category of R&D rather than a official product, but we've done an implementation where you can get an entire site running and serve it directly from your laptop to the internet, and it works, just using DNS and peer-to-peer networking, but it runs directly in the browser. And so if your laptop's open, it's serving the website, right? You don't have to deal with this huge towering stack. So people mainly come to it because it's faster and easier and less stuff to maintain.
Cool. Well, I think we'll call it on the questions because it's coming up to too late. It's 17 minutes past 8 here and 17 minutes past what, 1 a.m. for you, Brooklyn?
Yeah.
Yes. So thank you very much. I definitely enjoyed it a second time, and it's amazing to see something which is giving you like a different set of maxima to think about outside of our usual local maxima, and think about things that are, you know, so different to our usual stack.
Yeah.
So I'm sure a lot of people have got some new concepts and ideas out of it. So
Amazing.
thank you very much. We do have a few questions for the audience now for the JetBrains. So you can correct the answers. Oh, JetBrains. Yes, Francis is a big fan. You can see he's got the shirt there. So questions. So what does monotonic mean for functions? And you can give an example if you want as well for bonus points. First answer. Teutonic trick. Thanks, Francis. You won't get anything. Doesn't change direction. All right, Lord Teaspoon. That must be time for a renewal for one of your JetBrains, right? All right. So send me an email so I remember to send you the license. Yeah, it's renewal time in a new year. Very good. The JetBrains licenses are for a year, and yeah, you can use them for renewals or for a new product. Yeah, they're obviously not local. You still have to connect to the subscription server on those ones. Okay, and I'll give you another question. So, what's a technology that you can use for merging between the local copies that Brooklyn was talking about today? It's getting late, so it's not a very hard question. Sure, sync service. Not sure if that's the right one. Maybe it's part of the solution. Any other answers? Andrew's got disorder something. Francis has got auto merge. I don't know if you can win, Francis, if you're a co-organizer. Anyone want to chuck more things in there? Otherwise, I can give you a different question. Or at least it wasn't what I was fishing for. All right, I think that one was too hard. I was thinking the CRDTs was what I was thinking. Is that the right answer, Brooklyn?
Yep.
All right. Well,
yeah. Which auto merge is a CRDT, so you know. It's...
Well, do you want to claim?
No, I don't want to. I'm happy with it.
It's usually only for the non-organizers and speakers. All right. So, what was one of the ideals of the LoFi movement? There was 7, so just one. Maybe this one's too hard as well. It was hard to make up questions, Brooklyn, on your talk. Actually, everything was, you know, not just a simple thing. So
right.
Oh look,
oh.
We have a winner. Security and privacy by default. Here we go. So Earth Method, please send me a meetup message with your email address in it, and I'll send you the JetBrains license. And we have a second answer, but just slightly beaten. All right. Well, thank you very much, everyone. For next month, we have got a talk on .NET Aspire by Justin Yu. So stick around. Well, come back for that next month. And if anyone wants to give a talk, then you know we're very happy to hear from you. So drop us a meetup message if you've got something you'd like to talk about. So lots of thanks. Can you see the chat at all at this point? Good. Very good. People said fantastic talk and many thanks. So thank you very much, everyone, and we'll see you again next month.
Great.
Bye.
Thanks for having me.
It's been awesome.
Thank you.